about something called significant figures. All right, significant figures is a whole new kind of genre. You guys haven't talked about significant figures anywhere, have you? That term not ring a bell? All right. Significant figures are a way to basically count our digits to indicate how precise our measurement is. Okay? So not all of our figures or digits are significant in a measurement. So when I say significant figures, some people would say significant digits. We're talking about basically how many decimal places you take your measurement to. Okay? Or when you do math, including your measurements, how exact do you need to be within your measurement? Okay? So that's what significant figures or significant digits tell us. Okay? So when we take measurements, not all of our digits or our figures are significant. So we have some rules to follow about significant figures that tell us basically how far or how many decimal places that we should take our... Okay, so let's say that we use a meter stick, or in your case, the ruler I put in front of you, to measure something. Okay, let's say that we measure this pen to be 14.3 centimeters. So out of our 14.3 centimeter measurement, we have 3 valid or significant digits. 3 significant digits. 2 that we're sure of, and 1 that we estimated. So they read their instrument to about 14 centimeters. They found out it was somewhere between 14 and 15 centimeters, and they estimated that last digit to be 0.3. Okay, so on our measurement devices, our rulers that you have in front of you, you would expect to go to 2 decimal places if you're measuring in centimeters. If I were measuring in millimeters on my ruler here, how many decimal places would I go to? 1 decimal place. If I were measuring in millimeters, so I wanted to say this thing is 12 millimeters long, right? That'd be about 1.2 centimeters. But if I'm saying 12 millimeters long, I'm going to say maybe 12.1 millimeter. And I would estimate that last digit. Does that make sense? Can we see that on here a little bit? Okay, but we're estimating our last digit. But we see that we have 3 significant figures. Okay, so I'm going to give you lots of rules for how we determine how many significant figures are in measurements. Did you get what you needed here? Sorry, okay, I thought you wanted me to go back. Okay. So let's talk about what digits or what figures, right? I call them significant figures. What digits are considered significant? Okay, so any digit that is not a 0 is considered significant. Okay. Any digit that's not a 0 is considered significant. Okay. Significant figures have lots of rules about zeros, so you have to pay attention here to what the rules are. But they all kind of revolve around zeros. So you know anything that's not a 0 is going to be a significant digit, right? It's important in our measurement. Okay, zeros to the right of digits after the decimal point are significant. Zeros to the right of digits after the decimal point are significant. We are going to use significant figures a lot, so you need to become really, really good at significant figures. Okay, so can someone... let's look at an example of what this might be. Zeros to the right of digits after the decimal point. So this might be something like this, 8.00. Okay? So if I said something is 8.00 centimeters long, that means I read to this 0 and I estimated 1 more digit. Okay, so I think it's exactly 8.00 centimeters. So the fact that these are to the right of digits after the decimal point, those are significant. They are telling us it's not about 8, it's not around 8, it is exactly 8.00. Okay, so those are telling us an exact point. We might also have a situation that looks like this, 0.25 0. It's the same situation. We think it's not around 0.25, it's exactly 0.250. So these are because they are to the right of digits after the decimal point. Okay? So the rules get a little bit more complex with each one we add to it.
So then if you just put 0.25, that means it's about
0.25. We would say that we know that it's around 0.2. We think it's about 0.25. Right? If we add a 0 here, then that's saying we know the 2 and the 5 are right. We're estimating the 0. So the last digit is always the estimate. Does that make sense? So if we left it at 0.25, that would say we know it's somewhere between 0.2 and 0.3. We think it's about 0.25. If we add the 0, that's saying we know it's at 0.25. We're pretty sure it's at 0.250. Okay? Zeros between digits are significant. So these are just part of the number, right? Zeros between digits are significant. Okay, so here I have a mass measurement. 8,060.20 grams. How many significant figures do we think we have here? Anyone have a guess? Cece, what do you think? 6? How many of you agree with 6 significant figures? Very good. Okay, it is true. And this is why. We have a non-zero digit. That's significant. Non-zero digit, that's significant. Non-zero digit, that's significant. These are all zeros between digits, which means they are also significant. This 0 is to the right of the decimal point, and it's after digits have begun. So it's telling us it's exactly 0.20. So we have 1, 2, 3, 4, 5, 6 sig figs. Uh-huh.
So it's like the point.
Okay, so zeros to the left of digits before they start, whether they're before or after the decimal point, are non-significant. So in this example up here, how many significant figures do we see? How many of you think 4? Raise your hand. How many of you think 3? Raise your hand. How many of you think 2? 1? How many of you don't know? Okay. All right, there are 3 significant figures here, and this is why. First of all, our non-zero digits are significant. So the 8 and the 6 are both significant. The 0 right here is to the right of digits, and it's after the decimal point. So we're saying it's exactly 0.068 or 860. Okay, so this one is significant. These 2 zeros are not. Okay, let me write this a little bit bigger. 0.0860. These guys right here are non-significant. Okay, and let me kind of just show you about why that might be. Let's say that this was a length measurement, and I measured it to be 0.0860 centimeters. Couldn't I just say that I had, let's say, 0.860 millimeters instead? Can't I just change the unit to give myself a more appropriate number to get rid of those zeros? These zeros are just placeholders, and if I move it 1 more, I could give it a different unit. If I move it 3 more, I could say I have 860 micrometers. Okay? I can change the units to give myself a more appropriate number. So these zeros to the left of digits are just placeholders for that decimal point. We could change the unit to give ourselves a more appropriate number. Does that make sense? But the 0 here is still significant. It's still telling us we think it's exactly 0.860 or 0.0860. All right? Questions about that rule? I know that one's a tough one to remember, but left of the digits before any digits start are non-significant. Okay, all digits used in scientific notation are significant. All digits used in scientific notation are significant. And when we're looking at scientific notation, we mean only the visible digits. Okay, so what I mean by that is when I have a scientific notation, it looks like this, 1.420 times 10 to the 12th. I only mean these digits right here are significant. If I expanded the number, those would not be significant. I don't care what it looks like here. Okay, and I don't know how many zeros go with that, okay? But the expanded version is not counting here. We only care about these digits that are found right here. Okay, and those are all significant. Okay, can you think about a reason that they might be all significant? What has to be true about scientific notation and this number? Has to be between what? This number right here. This number has to be between 1 and 10. 1 and 10, right? So it can't have decimals to the left, or zeros to the left of the decimal place, because this has to be between 1 and 10. Okay? So let's say, how many significant figures do I have here? 4. Yeah, it's simple. 4. If I had one that looks like this, 8.040 times 10 to the negative 7th. Okay, I'm trying to express a really small number, but the number of significant figures that I have only matters about what I can see in scientific notation. So how many do I have? 4. Good. Okay. And if I had something that looks like this, 1 times 10 to the negative 6th, how many sig figs? 1. That's it. Okay. Make sense? Okay. So there's our concrete rules. Now we're going to move to some rules that we aren't quite as sure about. Okay, some numbers that we are a little bit unsure of. Okay, and these are called ambiguous numbers. If we are unsure about how many significant figures they have, we consider them ambiguous. Numbers. Ambiguous numbers are ones that have what I call trailing zeros, right? They have zeros at the end, but there's no decimal point, there's no scientific notation. We have no idea if this number is in the ballpark of 120,000 or it's exactly 120,000.00. Okay, so this number could have 2 significant figures, it could have 3, it could have 4, it could have 5. We don't know where the estimated digit is here. Okay, we don't know if it's 118,950 and they just round it up to 120, or if it's exactly 120,000.0000, right? We don't know. So this is considered an ambiguous number, okay? Could be 2, could be 6, could be 7, 8, we don't know for sure, okay? So you don't have to write this part down, but we just don't know, okay? So I'm going to give you a couple solutions to fix ambiguous numbers. So if I were to ask you, how many significant figures are in this number, you would just tell me it's ambiguous, right? I don't know how many. You don't have to give me all the possible options. You just tell me it's ambiguous. We don't know, okay? So there could be answers to some of your questions that are ambiguous, right? You just say ambiguous because we aren't sure, okay? So we use scientific notation to fix ambiguous numbers, or we add a decimal place. We add a decimal point to fix significant digits, to fix ambiguous numbers, Okay, we put it into scientific notation, or we add the decimal place to fix this, to put it in the correct number of significant figures if we know what that correct number is. Okay, if we know where the estimation was made, then we can tell if we need to put it in scientific notation or put it in significant figures. A decimal place. Fixes that you should use. How do you choose which of these fixes, the scientific notation or the decimal place? How do you go about choosing? Okay, if I had, basically I was trying to measure the mass of something, and the mass comes out to be about 119,500, and I round up to 120,000. Would I be better off fixing it using scientific notation, or fixing it by adding a decimal place and adding some zeros? What do you think would give me a more accurate depiction of my measurement? Yeah, scientific notation, right? That's because that's kind of a little bit more of a looser fit. So I might say that I have 1.20 times 10 to the, oops, to the fifth grams of my substance, okay? So that's giving me how many significant figures here? Good, 3 sig figs because we only look at the ones that are in scientific notation. So 1, 2, 3. So this is a good fix if we're not exactly sure where the estimation was made. If we just know we want to depict these numbers around 120,000, scientific notation is a good way to do that. If we need 5 sig figs, we could do it like this: 1.2000 times 10 to the fifth, and that would give us 5 significant figures. Okay, so you could use scientific notation to manipulate how many significant figures you need to show. Does that make sense? Because there are certain rules when we add and subtract that we'll get to about how many sig figs should be there. Okay, so if you need more, you can always add more in scientific notation. Okay, the other way that we could fix it might be with a decimal place. So I would say 120,000.00 or 120,000 just 0.0. Okay, I could do it a couple different ways depending on where my estimation took place. Okay, so my top one here, how many sig figs do we see in this top number? 8, right? All of these are significant. These are zeros that are to the right of digits after the decimal point, and these are basically become part of the number now. These zeros between digits become part of the number. Okay? Because these zeros are significant means the ones in the middle have to be as well. So then for my bottom number, how many sig figs would I have? 7, right? Because all I did was take away 1 0 here. Questions so far? When we're taking these measurements, and we have certain number of significant figures for our measurements, when we're taking our measurements and we're doing the math that goes with them, whether it's adding, subtracting, multiplying, and dividing, there's certain rules that you have to follow with your significant digits, significant figures. Okay, and I'm going to give you these rules for sig figs. So from now on in chemistry, you have to think about whenever you do math, we've got to take significant figures into account. Okay, so here's our first math rule for significant figures, and this is for adding and subtracting. So I want you to read through it and get it written down, and then I will talk through it and we'll do some examples. First of all, we need to determine what the least precise value means. Okay, so if I have two measurements here, 12.48 grams or 12.5 grams. Which of those gives me a more precise measurement? 12.48. So if I want to round to the least precise, that means I'm looking at decimal places. Okay, so I want to round my answer, so you might want to write this in there. Round my answer to the fewest number of decimal places. Okay, so least precise, we're talking about the number of decimal places here. So not as concerned necessarily with significant figures when we add and subtract. Okay, we're still using the significant figures method, but we're looking just at decimal places when we add and subtract. So let's look at an example here. Okay, I did the raw math for you. I'm not testing your adding and subtracting skills. Okay, we're looking at how the significant figures rules are applied here. So if I start with a value of 12.520 and I add it to 14.0, how many decimal places should my final answer have? It should have 1, because my least precise has 1 decimal place. and I'm going to round it to the fewest number or the least precise value I started with. So that means I need to round this number to 1 decimal place. Does 26.52 round up or down? 26.5, right? The 2 rounds down, so we're going to leave that with just as a 5. 26.5. Agreed? Okay, questions here? All right, very good. Okay, now our rule for multiplying and dividing is a little bit different. So read through that, and then I'll talk through and we'll look at some examples. Okay, so now instead of looking at decimal places when we multiply and divide, we're rounding to the same number of sig figs as the least precise. So we need to round, you might want to write this underneath, round to lowest or fewest, lowest number of sig figs. Okay, so we're going to round our answer to correspond to the fewest number of significant figures that we started with. Okay, so we'll look at our 2 values, determine which has the fewest number of sig figs, and we round our answer to that. Okay, so there's no way that our answer should ever be more precise than one of our measurements. That's the whole purpose of these math with sig figs, is that our answer should never be more precise than one of our measurements was. Okay, so let's look at an example here. Okay, 2.40 times 12. I did the math part for you. So since we're multiplying, we know we have to look at the number of sig figs. How many sig figs does this number have? 3. Very good. 2 is significant, 4 is significant, and the 0 is significant because it's to the right of digits after the decimal point. Okay, how many does this number have? 2. So that means our answer can only have how many significant figures? 2. So how do I make this into 2 sig figs? I'm going to round, right? I'm going to round to 29. Okay? I could also put it into scientific notation. Okay? And if I put it into scientific notation, it would look like this. 2.9 times 10 to the what? You have an idea? First. Good. First. 2.9 times 10 to the first. Okay? There's really no difference between those. They both have 2 sig figs, right? So you could take either one. When you're using your significant figures rule for multiplication and division, putting it in scientific notation sometimes becomes a necessity. Right? If our answer comes out to be 7,348 and we can only have 2 significant figures, then we have no choice but to put it into scientific notation. Kind of makes sense? Okay, we're going to work on scientific notation too, so if you're not super comfortable with that, that's okay, we'll work on it. But sometimes you have no choice but to put it into scientific notation.
So when you're doing that, like on the first one, when you have a decimal, it's not necessary to put it into scientific notation,
No.
but you can. But
Exactly.
then with that number, you have to.
Exactly.
Okay.
Exactly. You could always put answers into scientific notation and put the right sig figs and it would work. But for some of them, you just don't have to. Yep. Good question. All right, let's try. You think you can try them by yourself yet? I think so. Let's try these 2 on your own and we'll check them. Okay, so we had 319.7 for the raw answer. Does that match with the number of significant figures that we should have? No, it does not. Stone, do you know how many sig figs we should have in our answer here? 2. Good. Why do you think 2? Good. 2.3 only has 2 sig figs. We multiplied and divided. Okay, actually only multiplied here. We multiplied so we can only have the same number of significant figures as the fewest that we started with. Okay? So this only has 2 sig figs. How do I turn 319.7 into 2 sig figs? Scientific notation. Jenna, what do you think?
I have 3.2 times 10 squared.
3.2 times 10 to the second. That's okay. 3.2 times 10 to the second. That's perfect. Do we agree? Okay, why doesn't this work? Why doesn't this work? Oh, no, no, no. It's ambiguous. It's ambiguous. So I know it's tempting to say there's 3 sig figs here, but there's not. We don't know if it's around 320, which in this case it was, or if it was 320.0. So this is an ambiguous number. That's going to get like a sad face on your homework when you give me that, okay? Because some of you will. You'll still do that. And that's not how it works. This number does not have 2 significant figures. It does not have 3 significant figures. We don't know. This is what we want there. Okay? So that's what I was talking about when I said you sometimes might have to put into scientific notation. That was our only option. Okay? Leaving it here was not a good option. And why would I not say this? 3.1 times 10 to the second. Why would that not be our best option? Yeah, because this rounds up to a 3.2. This answer gives us a better depiction of our true answer than this one does. Okay, it's closer to 320 than to 310. All right? Questions there? Okay, very good. Let's see here. Brett, can you give me the raw answer for the second one?
26.281.
281. Okay, thank you. And let's see. Preston, do you think it matches the number of sig figs we're supposed to have? No, what should we have? Tell me how many decimal places, sorry. 1 decimal place, very good. So since we're adding, we should be looking at decimal places, not sig figs. Okay? So we should only have 1 decimal place because this one only has 1 and this one only has 1 decimal place. Okay? Which means our final answer should be, Sean, what do you think? 26.3. Very good. And it's 3 because this 8 rounds up. Very nice. This is our kind of standard form here. Sorry. Okay. M times 10 to the n power. Okay, that's the really, really basic form. So m must be between 1 and 10. Okay, so you can set it like that if that makes more sense to you. Right? M has to be between 1 and 10. The n value, the exponent value, is the exponent value ever a partial, a decimal number? No, you can never take anything to a 1.5 power, right? So that n number has to be a whole number. Can the exponent be negative?
Yes.
Yes. When do we see that our exponent in scientific notation is negative? Yeah, when I have a really small number. So when the number I'm trying to express is less than 1, my exponent should be negative. If the number I'm trying to express is greater than 10, my exponent is going to be positive. Okay? I know some people have a hard time remembering my exponent is going to be negative if I move to the left or move to the right. Okay, that method can get confusing if you're moving your decimal place and you're trying to remember the rule. Okay? What you need to understand is if the number I'm trying to express is less than 1, my exponent is going to be negative. The number I'm trying to express is greater than 10, my exponent is going to be positive. Okay, so really big numbers yield positive exponents. Really small numbers yield negative exponents. Okay. The reason we use scientific notation is it gives us a lot of freedom when we're expressing significant figures. So we already showed here that we can use scientific notation to give exactly 2 sig figs or exactly 3 sig figs or however we need, but it allows us a lot more freedom when we're working with significant figures. So I want to try and express this number in scientific notation. A 13,487,296.14. Okay, I want to put this into scientific notation. Okay, so let's think about, I'll kind of show you how I make this work. Okay, if I know that in scientific notation my M value has to be between 1 and 10. Where should the decimal place fall when I am expressing this in scientific notation? Between what? It should be between 1 and 3. Okay, so my new decimal place is going to have to sit right there. I move it 1, 2, 3, 4, 5, 6, 7 places to get back to my original decimal point. Okay, so I'm going to say 1.35. I'll just round right there. We'll talk about sign or significant figures here in just a second, but I'm going to round right there, and I'm going to say times 10 to the 7th. Okay, I don't care how many decimal places follow that original number. I only move it to get back to the original decimal point. Some people get tricked up there and they keep moving it to as many numbers that are as showing. That's not how it works. You move your decimal place from between 1 and 10 to the original decimal point. Does that make sense, kind of? Yeah, Jane.
If you wanted to like write out all those numbers, could you do that?
You could. Yeah. If I needed 12 sig figs, I could write out all those, or 8, or however many are there. I could do that. I don't have to round this number, but I can round it to put in the number of sig figs that I want. So this number right here has how many significant figures? 3. Good. Very good. Okay. All right, let's see here. What if I had a number that looked like this? I want you to put this into scientific notation with 2 sig figs. So put that number into scientific notation with 2 significant figures. So first of all, I'm going to put that decimal point where it needs to be between 1 and 10. And then I move it back to my original decimal point. So 1, 2, 3. Okay, so if I want 2 sig figs, what should this number read? 4.3, and it's times 10 to the what? Negative 3, very good, okay? Because I moved it from in between 1 and 10 back to the original decimal point. And my number that I'm trying to express right here is less than 1, which means I need a negative to go with my exponent there. Does that make sense? Feeling good about scientific notation? Okay, try just this last one on your own here. Right here. Okay, let's see. Connor, what do you think?
1.24 times 10 to the 5th.
24 times 10 to the 5th. Do we agree?
Yes.
Looks perfect. Okay, very nice. 1.24 times 10 to the 5th. I've got 3 significant figures. I didn't have to round up because my next number was a 2. Okay, so you do have to pay attention to that. If I ask you for a specific number of significant figures, you have to pay attention to rounding. Okay, I didn't need to round up because I had a 2 there. So very, very good. All right, let's move on to a little different portion here. We're going to finish up chapter 2 today. Okay, so this has to deal with accuracy and precision. Okay, we've talked about why measurements are used. We use them to quantify our observations. Now we're going to talk about how we evaluate those measurements. Okay, we use significant figures to display how precise they are or how exact a measurement is. But we're going to talk about now how to evaluate those measurements. Okay, and a whole kind of trial's worth of measurements. How do we evaluate those? Have the terms accuracy and precision been used before? Yes. Very good. Okay, good. All right, so precision. Can anyone tell me what precision means? What do you think? It's okay, you're on the right track. Okay, precision means we're looking to see how close together our measurements are. Okay, so how exact are our measurements? Okay, we have little variance. We're trying to have little variance within our group of numbers. Okay, our groups of measurements. Okay, so if we have a really precise group of measurements, that means there's not much variation within those numbers. So precision is how close together your measurements are. Accuracy is how close they are to the actual measurement, or the real, or the accepted value. Okay, those all kind of mean the same thing there. You guys probably have talked about density before. You don't have to write this down word for word, okay? But density we know is an intensive property, which means it does not matter how much of that substance is present. Right? It does not matter how much of that substance is present. Okay? The density of a certain compound or of a certain element or whatever is the same regardless of how much of that substance is there. Okay, and the equation for density is D equals mass over volume. Okay, D equals M over V. Mass could be measured in grams. It could be measured in kilograms. It doesn't really matter. Centigrams, whatever. Volume can be measured in milliliters, liters, cubic centimeters. Those are all volume units. Okay? So just go with what units you are given, as long as they are consistent. Okay, so if my density says that if my density value says my density is 1.24 grams per centimeter cubed, that means mass has to be measured in what unit? Grams. It has to match whatever your density is. Sorry, this is grams per centimeters cubed. Which means my volume has to be measured in what? Yeah, cubic centimeters, so centimeters cubed. Okay? It might be important for you to know that centimeters cubed are equal to milliliters. So 1 centimeter cubed is equal to 1 milliliter. You might write that down. That's a useful conversion, okay, that you might have to make. Okay, you might hear like people in the medical field ask for 12 cc's of something. Cc's means cubic centimeters. Okay, so really they're asking for 12 milliliters of something. But cc's comes out faster than milliliters. Right? All right. And density shows the compactness of matter. So if something's really dense, that means our atoms are really close together, right? And if something's not very dense, the atoms are farther apart. Okay, that's just kind of a basic definition of density, right? If something's really dense, that means our atoms are close together. There's not room for those water molecules or other types of molecules to get in there. They're really compact. If something's not very dense, there might be room for water molecules to get in, and that's why non-dense things tend to float. Right? That's very, very basic definition of density. We're solving here for volume, so we're not sure about what that is. So if we set up density equals mass over volume, we're going to go ahead and just plug our numbers in here. 3.21 equals 24.8 over V. Okay, do we know how to solve for this variable that's on the bottom here? What do we do with these? We're going to multiply by V on both sides. Then we need to divide by 3.21 on both sides. Okay, which means we're going to end up with volume equals 24.8 divided by 3.21. What'd you get? 7.7 what? And why did we round?
It's a significant figure.
Yeah, how many significant figures should our answer have? 3. We did a division problem here. Each of our starting numbers happen to have 3 sig figs, which means our answer can only have 3 sig figs. 3.73. And what are our units that go with this here?
Centimeters cubed.
Really?
Wait, milliliters.
Milliliters. Okay. So let me show you a shortcut here when we have this equation. If I have this equation and I'm solving for the variable that's on the bottom, all I need to do is switch these two places. Okay, that's essentially what we did, right? We multiplied by V, we divided by 3.21. All we're doing is switching these two places so that we end up with mass over density equals volume. Okay, so whenever you're solving for this bottom variable, all you need to do is switch the places of that with the one that's set equal to. Okay? Questions about that problem? I have 0.32 liters of a substance with a density of 2.19 grams per milliliter. What's the mass of the substance? Okay, does that have the correct number of significant figures? No, we need to have how many? We need to have 3 because 2.19 only has 3 sig figs. 701 grams. Very good.